I have always loved the term capture data. It's like data is some kind of wild animal, maybe in a swarm. Watch out for that data cloud on the horizon there, Bob. You'll want to take cover soon. We're going to have to capture that data one way or another. All joking mostly aside, we all know the value of capturing information in our everyday IoT wearable lives. But today we're talking about capturing data in an industrial setting. What then? Hi, I'm Amelia Dalton, host of Chalk Talk. Data capture does not have to include a net or some kind of fishing apparatus, but it can have a lot to do with temperature sensors. In this episode of Chalk Talk, Punya Prakash from Texas Instruments and I are discussing the challenges of high accuracy temperature sensors and how you can capture all the industrial information your heart desires with the right sensing technology. And before we get started, don't forget to click that link. There you can find even more information about temperature sensing solutions from Texas Instruments. Hi, Punya. Thank you so much for joining me.
Absolutely. Glad to be here, Amelia.
Okay, so before we jump into the details about sensor technology, let's discuss this at a top level a little bit. Now, why do we want to measure temperature in an industrial setting?
We know that the industrial market trends are driving towards more connectivity. The why behind that is to be able to capture more data. The data is then used to improve production capabilities, to be able to use the data to improve productivity, and ultimately to be able to drive more reliable systems. And as you look at what this data is, at the core of most systems is temperature measurement. Why do we do temperature measurement? Well, the temperature measurement, we can put it in three main buckets as you look at your applications. It could be around thermal protection, thermal monitoring for control applications, or even thermal compensation or calibration within applications.
So tell me a little bit more about some of these areas.
So, as we look at protection within systems, especially when you look at, say, automotive applications, where you have high-end FPGAs, ASICs, processors, you need an instant notification when your thermal boundaries of operations are either exceed or are in the negative range, too cold to operate.
Yes, there are a lot of expensive parts at a lot of times in these systems, and we don't want them to suddenly go bad on us, right?
Yes, absolutely. And as we discussed, reliability tends to be a very key factor, especially in automotive applications as well as within factories. As you look at pretty disruptive situations, if you see operation beyond thermal boundaries.
Every data sheet I've seen, the first thing I go to look at is the temperature range and if it's going to be good for my application or not.
There's also the impact of your performance. As you look at the data sheets, having more granularity into how does my device operate and is it operating efficiently, then dives into our monitoring and control aspect. A lot of applications have some level of thermal monitoring within the control loop. When you think about why, having that extra view into the accuracy around your application allows for your system to boost performance and maximize your thermal efficiency, including your performance of your overall system.
Right. And I also might need to turn fans on and off and do things like this based on the temperature my design is operating at.
Yes, absolutely. Take actions within the control loop to be able to go in and improve reliability of the system as well.
Sure.
So there's calibration, the third one we spoke about, and this is one of the least known application where we see thermal applications or sensors being used. When you look at, let's say, CMOS image sensors or pressure field transmitters, you have sensors or components within the system that can drift over temperature. And when you think of these sensitive components within your application, you need to use temperature sensors to be able to go in and correct for that offset and or compensate for that temperature drift which is why we see applications that tend to use temperature sensors within these applications to calibrate or compensate for drift errors.
Okay, cool. I hadn't really thought as much about that particular application. Now, temperature sensors have been around for a while. Certainly, there are a lot of options on the market that I've seen. Now, Punya, can you walk me through an overview of what kind of sensors are out there that I'm likely to run into, and tell me a little bit about how they work?
Absolutely, Amelia. As you look at the market, there are many types of temperature sensors that are available. As you look at most electronic applications, there are four basic types. You have the silicon based temperature sensors or the temperature sensor ICs.
Okay.
Thermistors, we have NTC based thermistors as well as PTC, positive slope thermistors. Then you have the resistive temperature detectors, or commonly known as the RTDs. And ultimately, you have thermocouples. And as you look at the various elements, you could pick either of these sensors based on your end applications. And as you pick and choose across these, say there are some important parameters that you need to consider to be able to balance the need of your ultimate system. Some of those are your operating temperature range. I think the basic selection process starts there.
Okay, like what?
If you need very high temperature support, by that I mean 2000 degrees C.
Very high temperature.
Very high temperature. And I think the choice at that point becomes very obvious. It tends to be more on the thermocouples. More often than not, accuracy is one of the key aspects of your selection process. And depending on that, you get to select one of the sensors. If you look at the silicon-based sensors, they tend to offer best accuracy. Thermistors can offer good accuracy, but they have a heavy dependency on calibration. RTDs tend to have the best accuracy as you look at the industry today across a wide temperature range. And then you have thermocouples, which also offer good accuracy.
Probably the best at 2300 Celsius, though?
Yes. And as you look at the linearity, it tends to be important because the behavior of your temperature accuracy, as well as your overall system, depends on how it varies over the wide temperature range. And when you look at the market today, it's silicon-based sensors and RTDs that offer the best linearity in the market.
Okay.
Then you get into the circuit and software complexity. This is where you spend a lot of your time as you look at designing and optimizing your end application based on the sensor that you select. And the easiest from a system design standpoint tends to be more on the silicon temperature sensors, while RTDs and thermocouples tend to get more complex.
Right. Okay. You mentioned with thermistors, calibration can be a big challenge in deploying a system.
Absolutely. And then you get into the topology, and this depends on what your end application is. With silicon-based temperature sensors, you have multiple options. It could be point-to-point, a multi-drop system. You can design a daisy chain application with multiple temperature sensors, versus when you look at some of the other choices, you tend to have a point-to-point system with your circuitry centered around that for your control loop or for your protection system.
Got it. Okay. Also, we are always looking at our BOMs, as everyone is, I'm sure. What are the price situations with these various options?
Yes, price tends to be one of the key factors as you look at your design consideration. RTDs and thermocouples tend to be more expensive. RTD, especially, they're made of platinum-based material, so they tend to be more expensive as you look at the component cost itself.
Right. I've had experience with that as well. Okay, back on the accuracy line. In some industrial applications I've worked on, accuracy has been a challenge. Now, what do you think are some of the biggest design challenges you see in high accuracy temperature sensing?
As we look at the temperature sensors we just discussed, thermistors and RTDs can offer high accuracy, and they tend to come with some trade-offs like calibration, system complexity, both around circuit and software, and ultimately power. Low power tends to be one of the key aspects of customers designing high accuracy systems. And that tends to be one of the key factors as you look at optimizing your design, addressing self-heating, as well as your overall system design.
Okay, cool. Now, from your list, NTC and RTD thermistors are the ones that I've seen used the most often. So tell me, what exactly is the deal with those?
Yes, so let's start with NTCs. They're essentially passive components and they change resistance with temperature. Very simple from a concept standpoint. And as you look at the temperature range, as you can see in the graph here, the resistance tends to reduce as temperature increases. And by monitoring that, you're able to go in and assess your temperature value in the overall system.
Yep, pretty simple.
They are relatively low in cost and they're very easy to source. On the other hand, these sensors tend to be nonlinear, especially as you look at the behavior across a wider temperature range. They come with an overhead of linearization, which, when you look at the overall system, provides a software overhead, which could either be in your memory requirements for the system or even the cycles, the MIPS, as you look at processing those.
Yep, you can see from the graph right there, not a line.
That line. But as you look at the overall system, especially tying it back to the high accuracy applications, there tend to be more components in your system. And truly determining the actual system accuracy tends to drive more complex circuitry. As you look at an NTC-based circuit, there are system level error contributors because as you look at this resistor that you're using in your circuitry, it has a dependency on several other aspects within the circuitry. For example, not only does your NTC have a tolerance and a beta value, it also needs a bias resistor, which can have a different tolerance or it could drift over temperature. You need a reference voltage. And ultimately, this analog data is fed into an ADC, which could inherit quantization error. And as you mentioned, they tend to not be linear. And when you do the linearization, there is an offset that is driven through that, which could contribute to the overall system error.
There are a lot of things, not just the sensor itself, that are conspiring to mess up my accuracy.
Yes. And you can see in the graph here, we're taking some examples of a 1% tolerance with a 1% beta. We're considering a 10K NTC with a 1% tolerance and a 1% beta to be able to go in and map this out. And you can see some different error contributors as you look at the linearization.
Okay. And what about RTDs? Do they have similar issues?
RTDs are very linear. So when you compare with an NTC, this tends to be the strength of an RTD.
Okay.
They are made up of pure material, which is typically platinum-based, can also be nickel or copper. And as you look at the accuracy, it's very predictable over a temperature range, which we like to see in high accuracy systems. And the error contributor does not come from that, comparing it to an NTC. They have a very low drift. And of course, it supports higher temperature range compared to silicon, all the way up to 600 degrees C.
I'm guessing that platinum contributes to that higher cost issue we talked about earlier.
Yes, it does. Now, as you look at the RTD behavior, they tend to change resistance over temperature. It's pretty small, but if you want to track that small delta, you tend to need higher precision measurement circuitry around it to be able to track that small delta change, which tends to add to the overall system complexity that we've been talking about. So as you look at these precision measurement circuitry, they tend to be more complex to design, but they also are higher cost as you look at the components itself. The precision bias, the reference resistor network, the circuit reference, the amplifier you need within this circuit, and even the ADC tend to be more higher precision to be able to extract the value from that.
Now, I can definitely see that my job in designing the circuitry around this is going to be more challenging. And I'm going to have to use higher precision components besides just my temperature sensor.
Absolutely. And very similar to the NTC circuit, as you look at the number of components within your circuitry, they tend to add their own error. So this does bring a more complex error analysis as you look at the overall system.
So my system level error can be accumulating greater than just what the temperature sensor is doing itself.
Yes. There's a maintenance cost to this. As we look at industrial applications that we highlighted earlier, maintenance is a very key aspect to it. And as you look at these RTD sensors, temperature sensors, they tend to be sensitive to drift off the acquisition circuitry, which typically tends to an annual calibration process. And this goes back to the maintenance aspect of an industrial IoT application space where we like to have minimal maintenance. So that may be another longevity consideration as you look at our customers.
We'd like to avoid rolling a truck once a year for every sensor we have out there.
Yes, exactly.
Okay, cool. That gives me some pretty good overview of NTC and RTD. But can you give me some guidance on how those would work out in industrial and medical applications?
Sure. So to kind of summarize, comparing an NTC and an RTD for industrial and medical applications, as you tie it into these specifically, an NTC thermistor can be accurate over a narrow temperature range, but as you look at a wider temperature range, there are additional aspects of driving that. For example, each of the NTC units need to be calibrated in production, adding a longer time to market as you drive high accuracy needs for these applications. The reliability for these low-cost components can be low. As you get into higher precision NTCs, they tend to increase in cost. They have a moderate software complexity. And as you look at the overall power, for better resolution, it tends to drive a self-heating, and they can be power hungry for those applications.
And what about RTD?
Yes, comparing that to an RTD, they are available in various accuracy grades, but they do require multiple calibration points to accurately measure the temperature. Due to self-heating of the metal, they tend to be power hungry. They offer accuracy across a wide temperature, which is very attractive in these industrial applications, especially field transmitters and metering, heat meter kind of applications. They also need complex circuitry and software for accurate measurement, and these components tend to be expensive.
Okay, so I understand the challenges you're talking about with both of those options, and it looks like both of them have some serious drawbacks. Are there alternatives we can talk about that would help me with my industrial design?
Absolutely. Let's talk about silicon temperature sensors first. So what are they? The concept is really simple. The silicon temperature sensors rely on the very predictive temperature dependence of a silicon bandgap. So if you look here, your change in voltage is directly proportional to the change in temperature. And we leverage this technology to be able to go in and develop our temperature sensors.
So, exactly the thing I don't like when I'm designing the silicon transistors we're taking advantage of here, right?
Exactly. Why does this help? Why does this matter? As you can see, because of the directly proportional nature of the silicon bandgap, you tend to have a very linear response. And when you translate that, you can have a guaranteed accuracy across the wide temperature range in which a silicon can operate. We have been able to achieve up to plus or minus 0.1 C accuracy. Because it's silicon-based, it can offer a wide range of integration. It can integrate ADCs, comparators, in some cases microcontrollers, HUMI sensors, amplifiers, interfaces, a varied options of interfaces. So as you can see, the overall system complexity can be reduced based on what the market needs for their end application.
Sure, there are lots of options to integrate it.
Yes. And that simplifies your design process for your end application.
Definitely.
It has a very low drift, and the overall system power, as you look at the circuitry that comes integrated, it tends to be very low power.
And I assume that means less self-heating, like you were talking about with the other options as well?
Yes, point on. And additionally, because you can integrate this, we are also able to tie them into very compact packages, giving an advantage of size. We just spoke about field transmitters. You highlighted that as one of the markets. And in field transmitters, they tend to be very sensitive to size. And as you look at how you're able to go in and drive a compact design, through the ability of us being able to integrate these various aspects of circuitry into one small packet size, you'll be able to optimize your design with a smaller footprint.
Okay, great.
And from a pricing standpoint, it's very comparable to similar accuracy technologies, especially as you look at your overall system cost and complexity and time to market. Now, this is based on silicon technology, so they tend to operate between minus 55 to 150 C. There are some parts that go up to 200 C, and that's kind of the limit in which they operate. But there are a lot of applications that operate within this temperature range, so we're able to go in and talk to those. And when you look at off-board PCBs, thermistors tend to have a huge portfolio of options, and we have very few packaging options to measure off-board PCBs.
Okay, walk me through how this helps me with my industrial or medical design challenges.
Texas Instruments recently announced the TMP 117 and TMP 117M.
And M stands for medical?
M for medical, which is our new highly accurate digital temperature sensor. By highly accurate, we can now achieve plus or minus 0.1 degrees C accuracy without calibration. With this being a digital temperature sensor, it integrates a lot of the system circuitry, which minimizes your software complexity as well as your system complexity. And given the low power technology, you're able to cut down your power consumption by up to 95%.
And that without the calibration part makes me very happy and my manufacturing as well. Okay, so since we're here to talk about high accuracy, let's dive into some details. Now, earlier you said RTD has the best linearity and accuracy. With the TMP 117, we are truly able to meet that AA accuracy across a wide temperature range?
Let's start with RTDs. Right? As you look at the RTD accuracy, the different classes of RTDs, you have the class A, class AA, and class B. When you look at the accuracy, it depends on the type of metal that's being used, and that drives a lot of the cost factors, but also a very reliable performance across the wide temperature range. Now, as we look at TMP 117, the TMP 117 delivers a plus or minus 0.1 C accuracy across a similar wide range of class AA without calibration or with zero calibration during the manufacturing process. And as we know, class AA RTD accuracy is used for several industrial applications like field transmitters, heat meters, where you're able to go and achieve this now.
Now, it makes it seem like we could replace RTD in an industrial setting, but let's talk about this in the context of medical applications. In medical, we have to meet ASTM E1112 and ISO 8601 for clinical temperature requirements.
So as you look at the ASTM E1112 or even the ISO 80601, which drives the temperature specs for the temperature specifications for the clinical temperature requirements, the TMP 117M offers 0.1 C from 30 C to 45 C and 0.2 for the range across 0 C all the way through 80 C. So as you look at the requirements for clinical accuracy, not only does it meet it, it also exceeds the spec by being able to go in and deliver this accuracy for the medical grade.
Yeah, and it looks like it delivers 0.1 over a wider range even than what ASTM has. And that's the range we care about the most.
Exactly.
Okay, I'm feeling comfortable with the accuracy now. Let's talk a little bit about the other challenges we mentioned, like calibration, system complexity, and low power. Now, how does this 117 compare with RTC and NTD in those areas?
Yes, Amelia, I think we started with defining the customer challenges centered around calibration, software and system complexity, and low power. And we spent a lot of time talking to accuracy. As you look at our high accuracy customers, their key care about starts with accuracy. That's what defines their application, defines their spec, defines their definition and system design.
Accuracy is sort of a go or no go kind of situation, right? If the accuracy isn't there, I can't start my design to begin with.
Absolutely. So, talking through that, we've been able to achieve 0.1C across a wide temperature range. This is the first device in the industry that offers 0.1C across a wide temperature range. Now that we've established that we can achieve and do this and support this reliably, the question is, as you look at some of the other challenges with an NTC-based thermistor or even an RTD, how does TMP117 stack up? So, talking through the design process, you typically start with your sensor selection, which at this point we've said, let's say 117 can achieve the 0.1C accuracy. Now, if you were to select an NTC or an RTD based sensor, either for your industrial or medical application, your process would start around not just picking the sensor, but also an ADC, a reference, a precision bias resistor, and of course, you have the pricing element as you look at your sensor selection. Now, with TMP117, the selection process starts with the sensor and ends with the sensor because it comes pretty integrated as you look at your other components.
On the others, I can see my BOM adding up already.
Yes. And then you start with, yes, you picked your components adding to your BOM, and then you get into your design consideration because it's not just the temperature range at this point, which is obviously a critical first step, as we mentioned earlier, but you also get into your other component contributors. It could be error, it could be just selection of those components. So you get into ADC. When you pick an ADC, you have the dynamic range of the ADC, the gain of a PGA, the reference current, filter design. You need to be able to account for the noise within your circuitry, your temperature drift for the other components, self-heating, which is a key aspect for NTC and RTD as we discussed, and ultimately the overall power consumption, not just for the sensor, but for your overall circuitry.
Looks like my job is going to get a lot easier with that TMP 117.
Yes. And then you get into your layout. As you look at an analog circuitry with an NTC or an RTD, you need to be able to go in and map out your trace impedance matching and carve out your thermal pathways and noise. When you look at thermal pathways, of course, the placement of the sensor is always a key factor in your thermal design, but you also need to account for how you're able to map this data back to your host controller. And as you account for the noise on your overall system, you have several more contributors versus for a TMP117, given it's a digital output, the consideration here is primarily your I2C line.
Got it. Okay.
And ultimately, you have the software. And as you look at how you collect the software, how you linearize, and ultimately your calibration process in the manufacturing, you have several different aspects to consider here. We look at ADC sampling rate. You have your IDAC, reference power down, linearization. And ultimately, with 117, you need to account for your software driver to be able to read the temperature data. And that's primarily the software that is needed. And we do have reference software to be able to enable this, which allows for a simple ease of use and enablement of your ultimate application.
And the lack of having to calibrate just in manufacturing alone has a tremendous advantage to us.
Yes, as you look at calibration, as you look at your process of manufacturing, it tends to be an overhead. And if you pick an NTC or an RTD, you cannot elevate that. It is an aspect of your manufacturing process. And if you remember, there is also a maintenance aspect as you look at RTDs, which means it's not just a production calibration, it is also a calibration as you look at the lifetime of the sensor through an annual process.
Right? Makes sense.
Texas Instruments offers the TMP117 EVM that you can order through Mouser.com or TIA.com. We have a very detailed application note that talks through your design challenge and experience and things to consider as you go in and design your wireless patient temperature monitoring application for medical, or as you consider replacing RTDs in your system for your industrial applications. It talks through the pros and cons, the trade-offs, how you should consider what aspects of your system design to ultimately allow selection as well as design through your manufacturing of your end application.
And it looks like you have a reference design for me as well.
So we have a flexible BLE patch with the TIDA 01624. Here, we document our process as we look at designing high accuracy temperature sensing on a flexible PCB, collecting the data through the digital interface, and communicating it through a BLE microcontroller.
Cool. A design that's going to have a lot of the same kind of challenges that I will have in a real world application.
Yes.
Punya, thank you so much for joining me today. It was a pleasure speaking with you, and I've learned a lot about temperature sensing.
Thank you so much. It was great to discuss not just TI's TMP117, but talk through your experiences in the market as you talk about your challenges in designing systems and how TI is able to, with the new TMP117, solve your design challenges as we look at your thermal challenges within the industrial application.
Great. Thank you so much.
Thank you.
And before we go, you didn't forget to click that link, did you? There you can find even more information about temperature sensing solutions from Texas Instruments. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. Can't miss it, right across the top. Or head on over to YouTube. Keyword EE Journal.